Let's give another minute or so. Get started. Hi everyone. Today we have Dr. Emilie Dunham as our guest speaker. Emilie received her BS degree in astronomy from Case Western Reserve University, and she received her PhD from Arizona State University. She is a NASA Earth and Science Fellow, and for her postdoctoral work, she's at UCLA right now, 51 Pegasi B Fellow. Apart from doing all her awesome research on CAIs and primitive meteorites, she's also a ultramarathon runner. So today she's going to talk about the meteorite implications for the galactic environment of solar system formation. Take it away, Emilie.
Thanks, Projecta, for your lovely introduction. And thanks everyone for being here today. And today I'm going to talk to you about how meteorites can inform us about the galactic environment of solar system formation. And if it's okay, I would ask that you please save your questions for the end or put them in the chat, unless there's a pressing word that I need to define. So let's get started. Also, this is work that I did for my PhD, and it could not have been accomplished without my wonderful collaborators listed down here. So I just wanted to thank you guys all for your mentorship and help. So I'm going to start out with the conclusion of my work, which is the star formation rate in the region before our solar system formed was about 4 to 5 times higher than the galactic average. So today, I hope to guide you through my research here and try to convince you that meteorites are very useful probes in learning about how the solar system formed and where it formed. So first, the motivation is to learn about the environment in which the solar system formed. To do that, I'm using isotopic probes in meteorite samples. And the methods I used were mass spectrometry. So I gathered a number of meteorite samples and took them to the mass spectrometer and measured them for multiple isotope systems listed down here. And with all this data, I performed a statistical analysis on it to figure out what it actually meant. And with that, I used the final results to inform astrophysical models. That brought me to the conclusion. So I'm going to start out at the biggest picture possible. So this is more than 4.6 billion years ago in a spiral galaxy. This spiral galaxy looks similar to our own Milky Way galaxy. And of course, the spiral arms are the most prominent features here. And these spiral arms are formed by density waves that go around the center of the galaxy. And these density waves compress gas and dust and really drive star formation. So as indicated by these arrows, the spiral arms, have a lot of star formation happening on them, which is why they're really bright, whereas most of the galaxy has very little star formation. And astronomical observations can predict the star formation rate in the regions of the galaxy, but these star formation rates that they can predict are over a very long time scale and from a very big area. So I hope to improve on this using meteorite probes. So now we're going to zoom in on one of these spiral arm dust lanes. So here you can see more clumping of gas and dust and brighter areas that indicate star formation, we'll keep zooming in to this molecular cloud. So a molecular cloud is an area in space that has a slightly higher density than the area around it. And a very big molecular cloud has a density something like 100 particles per centimeter cubed, and it's also very cold. And so in this cloud, you can see some big O stars, kind of like indicated, shown here. So an O star is very red in this image, and it's kind of veiled in some dust and gas, as are a lot of other stars in here. But these huge O stars are what form first. And they also die first. They only live for about 5 million years, much shorter than the lifetime of our own G star. And so once they live their life, they then explode as a supernova, and this explosion pollutes the area around them with the material that it ejects. So stars that form after these big stars will form with the material that the supernova ejected. And another thing that happens in an explosive supernova event is that there are a lot of galactic cosmic rays released, and these are high energy particles like protons that can travel across the molecular cloud. So what sort of material is expelled? So this is a periodic table that shows the origin of all the elements. And so, for example, Big Bang fusion creates hydrogen and helium, whereas dying and merging and exploding stars produce most of the other elements. And one more event that produces elements is cosmic ray fission. And I'll go through this a little bit more in a minute, but beryllium and boron are produced by this sort of process. And so in this talk, I'm going to be focusing on beryllium and boron and aluminum magnesium. So dying stars expel material, of course, and some of this material includes short-lived radionuclides. And these are isotopes which formed in the early solar system or were present in the early solar system, but have since decayed away because their half-lives are so short. They're not stable nuclides at all. Aluminum is, there's an isotope of aluminum called aluminum-26 that can be produced in supernovae or expelled in Wolf-Rayet winds. And this is one such short-lived radionuclide. So here I'm showing the parent, which is aluminum-26, and it decays to the daughter, magnesium-26, with a half-life of 0.7 million years. And so because it's so short of a half-life, so 50% of aluminum-26 will decay to magnesium-26 within this 0.7 million years. So there is no aluminum-26 that exists today, but we can measure excesses in the daughter product, magnesium-26, and correlate this to other, to aluminum over magnesium ratios as evidence that there was live aluminum-26 in the early solar system. And you can kind of think of this like a fossil, where a fossil tells people how the animal lived, when it lived, maybe where it lived. So magnesium-26 can tell us about the time frame of aluminum-26 and how it formed or originated. So this is how we actually go about calculating the initial aluminum-26 in the early solar system. This is a decay equation, and we create a plot where the y-axis is 26 over 24 magnesium, the x is 27 over 24 magnesium. So if we start with a pocket or an area of high temperature gas, and it starts to slowly cool, minerals will form out of that gas as solids, and they'll have different aluminum to magnesium ratios. So they will fall along this line. After some time, once aluminum-26 decays, the minerals will go along this line, where the slope is equivalent to the 26 aluminum over 27 aluminum ratio. So in this way, we can use the slope to infer how much aluminum 26 did exist in the early solar system. Another way to produce short-lived radionuclides is high-energy particle interactions. So one example here is beryllium-10, which decays to boron-10 with a half-life of 1.4 million years. And so here you can think of it like billiard balls, where you have a very high-energy particle, and this is accelerated towards an atom, or it collides with a larger atom. In this example, it's shown colliding with oxygen. And if the interaction is right, then the bigger atom can break apart into its constituent components. So beryllium-10 is one of the resulting nuclides from a collision like this. And similar to aluminum-26, beryllium-10 can also be inferred, or the existence of beryllium-10 in the early solar system can be inferred by creating one of these plots and analyzing solids that existed in the early solar system. So here the slope is equivalent to the initial abundance of beryllium-10. And so let's zoom out again to the big picture. We're still at more than 4.6 billion years ago, but this is a representation of the solar nebula in which our solar system was created. And so the solar nebula collapsed into a disk out of a pocket of a molecular cloud. And so the material in this disk is material from the molecular cloud, from the exploding supernova, and from also galactic chemical evolution, all mixed together. And right in this region, a very hot region near the star, solids started forming once the temperature went from a very high temperature down to about 1800 degrees C. So at that point, solids could form, and we call these solids CAIs, or calcium aluminum rich inclusions. So elements like aluminum and calcium are the first to condense into a solid out of a high temperature gas and dust mixture. And they form particles which can agglomerate into larger particles that are maybe a few microns in size. And these agglomerations can get bigger and bigger, and some of them actually can go through thermal processing. So they will get melted, and then the little parts of the agglomeration would kind of become a cohesive shape. And so also these CAIs can go through a process like evaporation, where some of the constituents might evaporate away because the CAI was heated. And just for reference, this sort of CAI, which is just an agglomeration of condensate materials, is called a fluffy type A or a compact type A. Fluffy because its shape is very irregular. And these ones are called type Bs. So here's an example of a big slice from Vigorano, which is a carbonaceous chondrite type meteorite. And so CAIs are usually white and oddly shaped. So if you could just take a second and look at this and see if you can find a few CAIs of your own in this slice. Okay, so I'm going to circle the ones that I found at least. Here are a lot of the weirdly shaped CAIs in Vigorano. And these CAIs, because they're the first solids to condense, they are kind of defined to be time zero of the solar system and formed about 4.56 billion years ago. And this is the expected mineral sequence of CAIs. And this is just due to how minerals condense from a hot gas. So the first thing to condense is a mineral called corundum. It's just aluminum oxide. And then after that, corundum will react with the surrounding gas to produce all of these minerals and all of these minerals together we find in CAIs. One that I'll be focusing on today is called melilite. And it's good for my study because it has a high beryllium to boron ratio. So it has a lot of beryllium and not very much boron. And so CAIs contain evidence of short-lived radionuclides, such as beryllium-10 and aluminum-26. So they recorded early events that happened in the solar system, or they contain the material that existed at that early time and can be a tracer for the events that happened that we no longer have evidence for today. So CAIs plus chondrules plus gas and dust plus a lot of other stuff in the solar system accreted together and went into producing planets and asteroids and everything we see today in the solar system. And we have a lot of meteorites as evidence for the different kinds of material out in the solar system, even asteroids. And so, but today I'm going to be focusing on carbonaceous chondrites, which are all boxed right here. And this is because carbonaceous chondrites have the majority of the CAIs that we can find. So there are subgroups of carbonaceous chondrites, which I will be talking about as well. Like down here, I'll focus on CO, CV, CR, and CH, and CB. They just have slightly different composition and slightly different abundances and populations of CAIs. So back to short-lived radionuclides, the motivating question behind a lot of my research here is how was beryllium-10 produced? Before I started measuring samples, there was evidence for the former presence of beryllium-10 in CAIs. The first evidence was about 20 years ago. And so in measuring more and more CAIs, we really want to know how much beryllium-10 is inferred to have been in the early solar system, because this will inform either of these two scenarios. So beryllium-10 could have been formed by irradiation in the parent molecular cloud. And so this happens when galactic cosmic rays, which are produced by supernovae and other astrophysical events, collide with oxygen in the molecular cloud to produce beryllium-10. And so when the molecular cloud collapses to form the solar nebula, this beryllium-10 is inherited and also mixed when it's collapsed into the cloud. So here we would expect there to be a uniform amount of beryllium-10 in the solar system. And so if we find that most CAIs have the same amount of beryllium-10, then we would probably go with this scenario. Whereas beryllium-10 can also be produced by radiation in the solar nebula. So here, the sun, right here, produces high energy particles called cosmic rays, and these can interact with oxygen in the solar nebula to also produce beryllium-10, which can get incorporated into CAIs. But this model suggests that the CAIs that are near the sun and a little bit farther from the sun, and CAIs forming at slightly different times, would get different concentrations of beryllium-10 just because of the kind of randomness of how the sun releases cosmic rays. So we would expect then that CAIs would have quite a range of beryllium-10. So I'm showing here a plot of beryllium-10 measured in CAIs from previous studies. So all of these data points represent one CAI. And right here, I'm showing the 10 beryllium over 9 beryllium ratio. So this is the an equivalent to the initial abundance of beryllium-10 in the early solar system. And I'm dividing the data up by the type of chondrite that the CAI was found in. And also here is a line indicating the level of initial 10 beryllium that existed in the molecular cloud when it collapsed. So just to show you some of the groupings, this is a group called FUN CAIs, and this stands for fractionation and unidentified nuclear effects. So this is just a special kind of CAI that has interesting isotopic anomalies and has, some interesting short-lived radionuclide data as well. So this is kind of a distinct population that could have been affected by evaporation, or it could have been formed in a weird place or time compared to the other CAIs. CHCb CAIs are also a little bit interesting because the CHCb parent body was produced in a very high impact scenario. So the body was disrupted before it got back together to form an asteroid. And so most CAIs that have been studied for beryllium-10 come from CV3 type chondrites, and a few have recently been measured from CO3 chondrites. So what I wanted to do was to measure more non-CV3 chondrites to see what the beryllium-10 abundance was in different kinds of meteorites. And also I wanted to correlate beryllium-10 with aluminum-26 because aluminum-26 can inform us about the timing of the CAI formation and also any alteration that it may have underwent. So to do this, I first went to the electron microprobe, and this is an instrument that allows you to image CAIs. This is called a backscatter electron image. I'll show a few more of them. But here, the brighter colors indicate larger nuclides. So here the brighter colors would be iron. This sort of image just informs us about the mineralogy of a specific CAI. And you can also do some spectroscopy on the electron microprobe to know the exact elemental composition of certain components of a CAI. Once I did that, I brought my samples to a secondary ion mass spectrometer. And so this is a schematic of one such mass spectrometer, and I'll just briefly describe how it works. So here is where the sample sits, and this is where the primary ion beam is produced, and that is focused on this column to hit the sample. So there's a little pit that's created by these primary ions, and then from this sputtering process, secondary ions from the sample are released from the sample and are guided through these lenses to focus the beam and other things, and then eventually to the magnet. So the magnet is, you can control the magnetic field, and this allows you to point specific masses towards the detector, which lies here. So that's how you measure isotopes, or one way to measure isotopes. And SIMS is beneficial because it's an in situ process where you have context, you can detect low concentrations, and you can have a small analysis spot. One thing to always be reminded of with SIMS is that during the sputtering process, some elements sputter more easily than others. So this has to be corrected for. So this is why we need standardization. So SIMS standardization is necessary because the true elemental and isotopic ratios in the sample can change when you actually measure them. So in this case, beryllium is ionized more efficiently than boron, so the beryllium to boron ratio must be corrected for using this formula of relative sensitivity factor. And so something that I needed to know before I even started my analyses is, does this factor change depending on the elemental concentration of the standard? So I've listed here a composition of my sample that has a very low beryllium and boron concentration. And here's a composition of a common standard that I've used. And you can see that it has a much higher concentration of beryllium and boron and way more silicon than my sample. So I wanted to make sure that this wasn't going to be a problem. So I made my own standard that had the composition of melilite, which is what I was measuring in my meteorite. To do this, I filled a platinum crucible with melilite composition powders, and then I put it in a furnace so that it could melt and then produce a glass. So this is just a fun little movie showing a sample that's up here in the furnace that's being dropped into a pool, into a container of water so that it quenches into a glass immediately. So I'll just play that again real quick. Yeah, so then we had to measure this glass. First, I used the electron microprobe to measure the major elements, and then used a different kind of mass spectrometer to measure beryllium and boron. So then I could bring it to the SIMS and see if how the standards matched up with common standards. So this here is the beryllium to boron ratio, ion ratio from the SIMS, whereas this is the beryllium to boron ratio that is the known ratio of the standards. So these down here are the common standards, and the blue ones are the 3 that I made using this furnace. And so I found that the glasses that I synthesized and that were of melilite composition and the common standards have the same RSF effectively. So this means that composition match standards are not necessary to determine accurate 10-9 beryllium ratios in CAIs with SIMS. So using these standards, I then went on to measure my samples. So this is an example of one of my samples from a CV3 chondrite. This one is called TS68. And so here, each of the different colors represents a different sample. So here's TS68 right here. And so each spot is one analysis point on the sample. And then the lines are the regression through the data points to find the slope. And the slope is really what we want here because it's equivalent to the initial beryllium-10 abundance. So here, most of the CAIs lie on this black regression line of 5.8 times 10 to the minus 4. But there are these 2 CAIs. This one's called CMS1 and this yellow one's called Lisa, that have quite different beryllium-10 abundances. And so here's another group of CAIs that are from CV3 reduced type chondrites. This one's called saguaro, which is in this bluish color. So yeah, here there don't seem to be any outliers really. All of the CAIs lie on this regression line that's a 10-9 beryllium ratio of 7.7 plus minus 0.8 times 10 to the minus 4. Oh, and just as a reminder, here on the y-axis is the 10 boron to 11 boron isotope ratio. And here on the x-axis is 9 beryllium over 11 boron. So 11 boron is the stable element. And so we draw this plot to calculate the slope. Here is the group of CR2 CAIs. Here's an example called yucca. It's this shape right here that has a melilite and a lot of spinel and some pyroxene. And so here, all of the data lie on a slope line 10-9 beryllium ratio of 7.5 plus minus 1.2 times 10 to the minus 4. And the next group is CO3 CAIs. So measured a bunch of them. And here's an example, Jemison, which is in this pink color. And it's also very mellow light rich with some spinel. And in this picture, you can see my SIMS pits. So these little holes right here are where the data points are on this plot. And again, the data mostly lie on one regression line of 8.5 plus minus 1.5 times 10 to the minus 4. And finally, we have the CHCB CAIs. Here's another example called THARP. And you can see the SIMS pits again. And also this CAI is also mellow light rich with a little bit of spinel. So that's a common theme of all of these CAIs. And here we have a similar regression line of 8.5 times 10 to the minus 4. Okay, and here are the aluminum magnesium isotope analyses. We looked at the aluminum magnesium ratio for 2 CV3 CAIs and 3 CR2 CAIs. And so most CAIs have a 26-27 aluminum ratio of about 5.2 times 10 to the minus 5. And so because we find that our CAIs have a ratio that's very similar, 5, 5.2, and all of these three put together is 4.5 times 10 to the minus 5, that our CAIs are very comparable to other CAIs and probably formed at about the same time and were not processed. So that's what the aluminum magnesium isotope systematics can tell us. So just right before I get more into statistics, I wanted to explain what MSWD is. So that's mean square weighted deviation. Some people call it reduced chi-squared. So if I'm showing the same plot here, just a cartoon version of boron isotope ratio versus 10 beryllium over 11 boron, if the MSWD is about 1, all of the data points will lie very nicely along the regression line or the slope 10-9 beryllium line. If the MSWD is much greater than 1, that means that there's quite a lot of scatter in the data and that the error bars do not really overlap the regression line for all the data points. And so in this case, an MSWD of 1, I would consider a valid regression, whereas this regression is not very robust. And yeah, so if the MSWD is too high, that indicates that there's less than a 5% likelihood that the regression is consistent with a line, or yeah. And one more thing I wanted to point out is that there are also errors on the MSWD that are indicated by the number of data points that you have. Okay, so here's the same previous data plot that I showed earlier with the 10 beryllium over 9 beryllium ratio on the y-axis. And so now I have circled a few data points in red that I've seen that to have a high MSWD, higher than the limit based on the number of data points in a regression. And so in reconsidering all of these regressions and determining the MSWD in a consistent way, and really trying to put together all the data from these different studies in using consistent methods, you can see that these high MSWD data points probably shouldn't be considered with all the other data just due to the scatter about the regression line. So now I have, for now, eliminated those high MSWD data points and added in my work, which is indicated in the blue. So yeah, same plot, grouped by the chondrite type that the CAI was found in. And so here I'm just going to compare my data against others' data. So for the fun CAIs, I only measured one fun CAI, and although it was a difficult analysis, the upper limit is consistent with other fun CAIs. And I also measured a very isotopically interesting CAI that has quite a high level of 10-9 beryllium. It's still consistent with most CAIs, but it's definitely different than the other fun CAIs. So that's something to consider. And for the CHCBs, my data is consistent with one other data point, but there's also this CAI from Fukuda et al. 2019 that has a ratio, I believe, around 60 times 10 to the minus 4, way up there. So my data is not consistent with that. My blue data is consistent with other CV3 oxidized CAIs and also other CV3 reduced CAIs. There's one outlier here that I'll talk about in a minute. And CR2 and CO3 CAIs also fall within the same, have a similar abundance of beryllium-10 than the CV3s, except there is this previous study of a CO3 CAI that has a much higher 10-9 beryllium ratio of about 29. So we'll definitely have to think about that later. But this one is CAI Lisa that I talked about a little bit before. And so we think that there may be a reason why it has this high 10-9 beryllium ratio, and I will attempt to explain it to you now. So CAI Lisa was measured by another study for a number of isotopes, including samarium 150. And so it has a very high level of this isotope compared to other CAIs, which indicates that it likely existed near the surface of the asteroid, which was its parent body. So the scenario could kind of go like this. You have a galactic cosmic ray that hits the surface of a Lisa CV3 parent body and interacts with oxygen near the surface. And this produces protons and neutrons, and some of these neutrons can be really fast and thermalized. And so this is what actually produces the excess 150 samarium, because the neutrons collide with 149 samarium, and because of the interaction produces 150 samarium. So that's why we think this meteorite or the CAI could have that high level. But because the interaction also produces protons, these can collide with oxygen to create extra boron and beryllium. And because the concentration of boron is so low in CAIs, especially mellowlite, the boron excess created by this process could actually elevate the 10-9 beryllium ratio artificially. So how this would work is shown here. This is the same plot where the slope is the 10-9 beryllium ratio. So the black data points are what I actually measured on the SIMS. And from that, we tried to back calculate what that would mean in context of this idea. So if you subtract some boron from the original data, only 2.5 parts per billion, you can actually move the data points to the gray data points and produce a slope that's about 13 plus minus 6 times 10 to the minus 3, times 10 to the minus 4. And this is kind of cool because it says that maybe Lisa started out as having a more normal, or around 7 times 10 to the minus 4, 10-9 beryllium ratio. But then once it was irradiated, there was some extra boron added to artificially elevate the slope. So although we can't prove this for sure, this is a reason to call Lisa an outlier. and eliminate it from the larger discussion. So now I'm showing the compiled data without Lisa, and again you can see that most of the CAIs are about at the same level, except for funds and a few outliers. So now I'm going to show you how I statistically analyzed the data to see actually if the CAIs all have the same number of 10/9 beryllium. So as an example of this, I'll just go through the CV3 oxidized group. So I measured 6 CAIs in the CV3 oxidized group, and I calculated that together they have a weighted mean 10/9 beryllium ratio of 6.2 with a standard error of 0.7. Now these, considering this together, they have an MSWD of 1.2, where the allowed MSWD is 2.3. So because of the low, or of the MSWD that's close to 1, we can say that all the CV3 oxidized CAIs have, are distributed evenly around the mean, and so they all have the same 10/9 beryllium ratio statistically. And this works also for CV3 reduced CAIs, for CR2s and CO3s. They all have MSWDs that are lower than the allowed MSWD. But this does not work for CHCBs and fun CAIs. They have quite a high MSWD, which indicates that a few CHCBs and the few fun CAIs measured have quite a variable range of beryllium-10. And if I put most CAIs together, which is 42 CAIs, I calculate a 10/9 beryllium ratio of 7 plus minus 0.2 times 10 to the minus 4. This is a weighted mean again. And the MSWD of this group is 1.3, where the limit is 1.4. So that means that most CAIs, this is not including the CHCBs, funds, and plaques, which have, the few of them have variable ratio. So that means that most CAIs have this a level of 10/9 beryllium. So so another way to look at the data is to correlate beryllium-10 to aluminum-26. And this data isn't really conclusive yet, but I'll just say that if beryllium-10 and aluminum-26 formed or were in a CAI together at the same time and decayed together, all of the data should lie along this concordant decay line. But it kind of falls into these different populations, some of which are on the concordant decay line, but some of which are outliers. So we can't really say if aluminum-26 and beryllium-10 are concordant or not. They're likely not. So back to the discussion, what does this 10/9 beryllium ratio mean for the origin of beryllium-10? So if it was produced in the nebula where the sun is emitting cosmic rays, then the beryllium-10 would have a variable ratio, or have beryllium-10 in CAIs would be quite variable. And Jacquet et al. 2019 modeled that the beryllium-10 would decrease as you go out from the sun by quite a lot, and it would also increase with time. And because this is only observed in 2 CAIs out of the almost 50 that have been measured, we think that this is not the main way that beryllium-10 is produced. We think that inheritance is the main way beryllium-10 is produced. So this is when it's made in the molecular cloud and then inherited into the solar nebula. But the beryllium 10/9 ratio in the average galaxy produced by galactic cosmic rays is less than 2 times 10 to the minus 4, whereas I'm measuring a ratio of 7. So this implies that the area in which the molecular cloud was experiencing more galactic cosmic rays than an average region of the galaxy. So this implies that our sun formed in a region that had a higher star formation rate than the solar system is in right now. And because this 7 times 10 to the minus 4 initial ratio is observed in most CAIs, we think that this is the main way that beryllium-10 is formed. So this is so to prove or to say this more definitively, we worked with a modeler, Yusuke Fujimoto, and we modeled how the galactic cosmic ray flux is distributed in a galaxy. So these probability density curves show the galactic cosmic ray fluence near a new star in orange and in the average galaxy in blue. And the crosses indicate the median probability. So this plot says that 50% of new stars form in a region where the star formation rate is higher by 3.7 times than the average galaxy. And to put this in perspective for beryllium-10 and go through a calculation, this implies that there's a 40% probability that near a new star, the 10-9 beryllium ratio will be 7 times 10 to the minus 4. So the model works according to our data. So this is just a concluding plot, and I'll go through it with you. So this, again, is the 10-9 beryllium ratio, and all the CAIs divided into the chondrite groups, where the black data points are from my study. So the galactic average is this line down here. And then I think that most CAI, or all CAIs, inherit this beryllium-10 produced from the molecular cloud at a level of 7 times 10 to the minus 4. Some CAIs can then be thermally processed, like the funds down here, to find a reduced level of 10-9 beryllium of 4.6 times 10 to the minus 4, because during evaporation you could lose boron. And then there are a few CAIs. Here's Lisa, and here's the interesting CHCb CAI and the interesting CO3 one. And this shows that there are a few higher values in CAIs that could indicate that there was extra solar or parent body irradiation that's overprinted on the initial inherited level. So to put this in pictographic form, we start with our spiral galaxy with 10-9 beryllium ratio less than 2 times 10 to the minus 4 in the spatially averaged galaxy by galactic cosmic rays. Then the pocket of the molecular cloud collapses in a high star formation region that has 10-9 beryllium of 7 times 10 to the minus 4 because of how the galactic cosmic rays interact in the cloud. And then all of this is inherited into the forming solar system. So 85% of CAIs, according to this study, have been have 10-9 beryllium ratio of about 7 times 10 to the minus 4, which implies that 85% of CAIs have the inherited level of beryllium-10. And then, so the CAIs were formed there. And so some of them could have been processed and have an artificially lower value of 10-9 beryllium. And then there are also a few higher CAIs, just 3, that could have a higher 10-9 beryllium ratio due to solar or parent body irradiation. So that's the conclusion of my talk. Thank you, and I'm happy to take questions for the rest of the time.
Great, awesome talk. Are there questions from the audience? You could either unmute and ask your question or type it in the chat window so that either I or Emilie can read it out loud. Okay, Maitreyi has a question. Can you say something about the gas in the high star formation region?
Do you mean like about the composition of the gas? Or about the anything? Okay, so yeah, I can go back to my last chart. Yeah, so the regions of gas in the spiral arms are slightly denser, and this is how the spiral arms, or why the spiral arms have so much more star formation. And so they're more dense, and this also makes them more hot. So stars are more likely to form there. But the gas probably has the same composition as everywhere else, but it's just dense due to the density waves the spiral arms make.
Okay, we have another question. Could you relate the last chart with your star formation hypothesis?
I don't know exactly what he wants me to do, or she, but do you mean this summary chart? So I guess I'm not really making a star formation hypothesis, but more of a hypothesis about where with what material our solar system formed with.
Oh, the question was about.
Okay, so there's more star formation before our solar system formed. It's more about where. So our when the solar system was formed, it was likely in one of these spiral arms where there was a lot of star formation. But now our solar system is in a more quiet region just because of how we've moved around the center of the galaxy, so that we're no longer in a very active region compared to where we were 4.5 billion years ago.
Okay, we have a question from Nicole. For the CAI that was near the surface of the CV3 chondrite parent body, which CV3 did that CAI come from? And does that meteorite have other evidence that it might be a regolith breccia?
That's a good question. So yeah, it came from a meteorite called NWA 6991. And the size of the meteorite is very small. So it's kind of hard to have much context for what it actually looks like. I think the piece is like, I don't know, pebble sized or something. But I don't have any evidence that it would have been a regolith. And just because it's a pretty accreted CV3 chondrite, but galactic cosmic rays can penetrate a few meters into the surface of a parent body, so it could have just been a little bit below the regolith, although I don't know how deep the regolith would have been.
Okay, are there any more questions from the audience? You can also unmute yourself and ask your question. All right, if not, let's thank Emilie for giving this amazing talk, and thank you all for attending today.
Thanks for your attention. It was great talking to you.